We're going to start by finding an equation for this plane. To do that, we will put our pyramid in this space with respect to our three axes. We'll put the base of the pyramid here in the xy plane, and A will be at the origin. We'll put B over here on the x-axis. When drawing in 3 dimensions, make sure all of your lines are parallel. This is C. Its x-coordinate is the same as B, that's 4. The y-coordinate is 4 and the z-coordinate is 0. And over here, this is D. The vertex E is directly above the center of the square, which I'm calling O. Here's E up here. Its x and y coordinates are 2 and 2. So let's find the z coordinate of our point E. All these side lengths are 4, so EC is 4. I'll draw this altitude. We'll call this S. It's halfway between B and C, so its coordinates are 4, 2, 0, and this distance from S to C is 2. This is 30, 60, 90, so ES is 2 root 3. O again is the center of our square. The distance from O to S is also 2. And now we can use the Pythagorean theorem to find the distance from E to O, or the height of our pyramid. So our z coordinate is 2 root 2. The 3 midpoints described in the problem statement, I'll label them R, S, and T. We already have S here as the midpoint of BC. T is over here, the midpoint of CD. The x-coordinate is 2, y is 4, and z is 0. R is the midpoint of segment AE, so it's just midway between the origin and 2, 2, 2 root 2. So its coordinates are 1, 1, and root 2. 3 points are enough to determine a plane. A plane in 3 dimensions can be described by an equation that looks like this. So we'll plug in these 3 points in turn and solve for the values of these coefficients. Here x is 1, y is 1, and z is root 2. First, we'll subtract the third equation from the second, and we have that A and B are the same. Plugging this back into equation 3 gives us D is 6A. Plugging this into equation 1 and doing this substitution and solving for C, it's 2 root 2 times A. We'll choose A is equal to 1 for our plane equation. This gives us x plus y plus 2 root 2 times z is equal to 6. Let's redraw our pyramid. Here's our base, A, B, C, D. Our vertex E is on top. Here are midpoints R, S, and T. Our plane is going to have a couple of other intersecting points through the pyramid. These will occur at segments BE and DE. We'll call these 2 points U and V somewhere on these segments. So U is the intersection of BE and our plane, and V is the intersection of DE and the plane. We can also note that there is some symmetry on either side of this diagonal AC, so we can take advantage of that. Let's figure out the coordinates of U. To do that, we need to find an equation for the line that passes through segment BE in 3 dimensions. We do that using vectors. First, I'll find the direction vector for our line from B to E. The x-coordinate goes down by 2, so that's a minus 2. Here, y is plus 2. And z is plus 2 root 2. We can factor out a 2 from these 3 numbers, and since we'll be using this as our direction vector, the magnitude is not important, so we'll just use this smaller vector. So the line that contains segment BE, we can write it this way, starting at point 4, 0, 0, plus some factor times this direction vector. This is basically the 3D equivalent of the point slope form, where we replace the slope with this direction vector in 3 dimensions. Adding these 2, this means that any point on segment BE will have coordinates that look like this for any value of t. And we're trying to find U, so we're going to see where this intersects our plane with this equation. So we'll plug in our values of x, y, and z into our plane equation. Here's x, y, and z. And when we solve for t, we get 1/2. So that is the value of U. The x-coordinate of U, we subtract 1/2 from 4. The y-coordinate is 1/2, and z is root 2 over 2. Taking a look back here at our diagram, again, because we are symmetric about this segment AC and our square is in the xy plane, we note that V is going to have the same y coordinate as U, that's root 2 over 2, and the x and y coordinates are just the reverse of those of U. So the x coordinate of V is 1/2 and the y coordinate of V is 7/2. Now we have our 5 intersecting points of the plane with the pyramid, and the problem asks for the area of this pentagon. Let's sketch the pentagon again. again here. R is here, and then we have U and V, and then S and T. And we'll collect all the coordinates again. Let's find the distance between these side lengths using the distance formula. Again, this pentagon is symmetric, so RU is going to be the same as RV. So these two distances are root 7. These are root 3, and this distance is 2 root 2. If I draw UV, I can break up this pentagon into an isosceles triangle and an isosceles trapezoid. So let's find the distance from U to V. That's 3 root 2. We'll start by finding the area of isosceles triangle RUV. This side length is root 7. I'll draw this altitude from R. Half of the base is 3 root 2 over 2. Let's find the height. So the area of this triangle is 3 root 5 over 2. And now we'll do the trapezoid. We've got our two bases, so let's find the height. I'll drop this altitude, and since it's isosceles, TW is just half the difference of the two bases. We'll use Pythagorean theorem to find the height. It's actually the same as what we had for our triangle. And now we'll use our formula for the area of a trapezoid. It's the average of the bases times the height, or 5 root 5 over 2. And again, we're adding these two areas to get 4 root 5. We'll put everything underneath the radical, so this is 80, and the format of the answer. The problem asks for the value of P, so our answer is 80. If you'd like me to solve any other math contest problems, please leave them in the comments.